What if the biggest bottleneck in robot generalization isn't the action decoder, but where the model actually looks? Current vision language action models are notoriously brittle. Throw them a new object, a cluttered table, or a completely different robot arm, and their attention scatters across the background, the robot's own limbs, or random visual noise. They learn low-level visual shortcuts instead of manipulation logic. But a new architecture called Pelican-VLA 0.5 flips this script. It forces the model to attend before it acts. And the result is a form of attention-level generalization that emerges purely from pre-training, without object masks, segmentation labels, or task-specific fine-tuning. Let's break down why this matters. VLA models map visual observations and language instructions directly to robot control signals. The goal is zero-shot manipulation. Train on a dataset, deploy on a new robot, and it just works. In practice, the action pathway in most VLAs attends diffusely. It doesn't know what to look at, so it guesses, often relying on environmental noise that breaks the moment the scene shifts. Recent work suggests that generalization depends heavily on how task-relevant information is routed before action prediction. Pelican-VLA 0.5 takes this seriously by inserting a compact, learnable interface between perception and action. The model is built on a shared QN3VL4B backbone, but the architecture is structured around 4 contiguous token segments. First, a vision language prefix that encodes the current scene and instruction using bidirectional attention. Second, a middle segment of temporal cosmos, latent tokens that capture short-term dynamics. Third, and most importantly, a set of 32 learnable reasoning slots. And fourth, a suffix containing proprioceptive state and noisy action chunks for flow matching. Here's the critical constraint. The action pathway is explicitly blocked from directly attending to the dense visual tokens. It can only read perception through those 32 reasoning slots. Think of the slots as a narrow, learnable bottleneck. They query the upstream context, compress manipulation-relevant information, and pass a distilled representation to the action generator. This forces the model to answer the question of what to act on before it even starts predicting control signals. But a bottleneck only works if the model can't just bypass it. Pelican-VLA 0.5 enforces this through 3 mechanisms. First, a curriculum attention mask. During early training, the action tokens are allowed to attend directly to the visual context. Over the first 10,000 steps, this hard constraint is gradually applied, shifting perception to action communication entirely through the slots. Second, an orthogonality regularizer. If all 32 slots collapse into representing the same thing, the bottleneck is useless. The model is penalized when the slot gram matrix deviates from the identity matrix, forcing each slot to capture distinct factors of the scene, task, or action context. Third, a slot-gated generation head. The pooled slot output modulates the future frame prediction branch, tying the bottleneck representation to forward predictive, action-relevant structure rather than static appearance. The training objective combines several losses. You have the standard flow-matching action loss, which predicts delta action chunks by denoising Gaussian noise along a continuous trajectory. You have a future frame generation loss in the frozen cosmos latent space, which gives the model a compact dynamics signal without the instability of pixel reconstruction. And you have a slot language contrastive alignment objective. This uses a symmetric info and CE loss to align trajectory embeddings with language instructions, making the slot representation more controllable by natural language rather than just visual salience. Now, does this actually work, or is it just architectural overfitting? The authors ran a rigorous ablation. They held the data, optimizer, and parameter budget completely fixed, and swapped the slot architecture for a dense mixture of transformers baseline. The dense model fit the action loss just fine, but its attention remained diffuse. Pelican-VLA 0.5, however, developed concentrated, object-centric attention patterns around instruction-relevant regions. This proves the effect is architectural, not data-driven. When they tracked attention dynamics across training checkpoints, they found a 2-stage emergence. Early in training, the slots localized to visually dominant objects regardless of the instruction. Only after introducing the contrastive language loss does the attention become language-conditioned. Change the prompt from pick up the black bowl to open the drawer, and the attention shifts accordingly. Over time, as pre-training progresses, attention alignment with the target object increases significantly, even after the action loss plateaus. This shows the representation is reorganizing independently of pure action fitting. On the RoboTwin benchmark, after fine-tuning, Pelican-VLA 0.5 hits 91.4% success on the clean setting and 91% on the randomized setting, outperforming other open-source VLAs. But the real test is zero-shot. Deployed directly on unseen scenes, novel objects, and a new robot embodiment without any fine-tuning, the policy consistently approaches the correct instruction-relevant object and produces coherent, goal-directed motions. It doesn't just flail. However, success rates remain low in strict zero-shot mode. The robot reliably picks the right object, but struggles with fine-grained control like stable grasping and precise placement. They also deployed it on a real-time humanoid for a tabletop cleanup task. After fine-tuning on teleoperated demonstrations, it achieved an 80% success rate, handling long-horizon manipulation, repeated object selection, and real-world sensing noise robustly. This brings us to the core insight of the paper. Fine-tuning Pelican-VLA 0.5 does not create manipulation-centric attention from scratch. Attention visualizations and representation similarity analysis show that the zero-shot and fine-tuned models attend to nearly identical regions. The slot representations remain highly aligned. What fine-tuning actually does is strengthen the mapping from these preformed, manipulation-centric attention regions to executable actions. The model already knows what to look at. It just hasn't fully learned how to act on it reliably across new embodiments. The authors call this the representation-to-action gap. Why does this gap exist? Primarily data scale and action parameterization. Pelican-VLA 0.5 was trained on roughly 2,400 hours of heterogeneous data, which is actually an undertrained regime. More importantly, it uses joint position actions, which are highly embodiment-specific. Cross-embodiment transfer suffers when the action space does abstract away from the specific kinematics of the training robots. The team is already planning a stronger checkpoint trained on approximately 7,000 hours of data, alongside improved action parameterizations that will likely close this gap significantly. Pelican-VLA 0.5 isn't a magic bullet for zero-shot manipulation yet. It's a crucial intermediate step. It proves that routing perception through a compact, learnable bottleneck can induce robust, language-conditioned, manipulation-centric attention during pre-training. It shifts the bottleneck from the data to the architecture, and it clearly maps out what's left to solve: scaling data, refining action spaces, and bridging that final representation-to-action gap. If you want to dive into the architecture, check out the pre-trained weights, the attention visualization tools, and the full code on GitHub. The path toward truly generalizable robot policies is being built one slot at a time.